Students, welcome to lecture number 9. So, we are almost 1/4 of the course done. So, today we are going to discuss more about ensemble learning. As you know, we are talking about the topics on materials informatics in action. So, what are the different models used for material informatics? This is the main theme of discussion for the last lecture also, today's lecture also. And in the last lecture I discussed about gradient descent problem or gradient descent methodology. Today we are going to talk about ensemble learning. What is ensemble learning, how it is done, what are the different sub methods of ensemble learning. That is what we are going to discuss in the lecture today. But so that means we are in the second part of this course, where we are talking about the various kinds of ML models. And first we have discussed the gradient descent. Obviously, before that we already discussed about the problems of probability classification, Bayesian algorithm, as well as regression methodology. So, we are already into the business of different kinds of models. Okay. Slowly we will get into other models also, but let us talk about the ensemble learning today. Before that, let us do some recap of whatever we learned in a very short span of time. As you know, gradient descent algorithm is very important in machine learning, because whatever modeling you do or you carry out, you are going to incur some kind of errors. Obviously, one cannot predict 100% whatever is actually observed. So, we have always some kind of a level of prediction, 90%, 92%, 93, 94, 95. I think that is what we always aim to achieve in our modeling. And so, therefore, there is always some error between the predicted value and the actual value which is observed in real life. So, this error needs to be minimized for the betterment of prediction. And how we can minimize the error? By using this technique called gradient descent algorithm. And what is this technique? As you know, this algorithm is basically dealt with the problems by best solution to the problem by making small adjustment in the right direction. This is a very important statement. How do you do that? Let us talk about a hill, and we want to find out the lowest point of the hill by walking down the slope step by step. When you are at the top of the hill, you can't see where exactly the lowest point. So, you always take down the slope. Now, you have different pathways to reach that lowest point when you go to the down the slope from the hill, and you need to take the best path, the path which will lead to the lowest point, as well as the path which will be steepest, so that you can reach as quickly as possible. But when you reach that, when you move along the path, you are going to take step size, right. Some may walk fast, some may walk slow, some may walk very fast. So, depending on this walking rate or moving rate, we can always talk about what is known as a learning rate in case of machine learning. That is a big hyperparameter in gradient descent problem or gradient descent algorithm I talked about in last lecture. So, we discussed the gradient is nothing but a slope, right, the first derivative of any function. If f(x) is a function, f dot is the slope, right. The slope can vary depending on the location of the curve, also depending on the direction in which it is measured. So, it is there in the mathematical mathematics books that how vectorial way of depicting the slope variation as a function of direction. So, in this context, we always talk about functions. We do not talk about straight lines, because straight lines are much easy to handle. When you use a function, gradient provides the vital information of the rate of change of the function's output with respect to the changes in the input. That means, f x prime x is nothing but df x by dx, or rather I can write down d by dx into f x, right. So, this d by dx is an operator. it tells you rate of change of the function fx with respect to x. So, this is what is the important aspect you need to remember when you talk about gradient. So, we go to the top of the hill, start with random guess when you are dealing with certain functions, that is what is the meaning of top of the hill, and then you have to feel the slope. You have to look around and see which is the direction in which the ground is sloping down. That means you have to calculate the gradient and different directions, right, and then decide which is the steepest way of downfall or steepest way of moving down the hill, right, sorry, not downfall, down the hill, which is the steepest way, okay, of downhill, right. And the step 3, you simply move with the direction in the slope is steepest, but you always take the step in such a way, the step means you have to take the learning rate in such a way that you reach your destination. So, therefore, in the step 4 you repeat the whole thing if you are not able to reach your destination, correct. So, gradient descent moves towards the bottom or the minimum of a loss or error functions that represents what is the minimum error, right. You want to reach that level, that is why we use this technique. And how it is done? Simply it is done to minimize the cost functions of any model by iteratively adjusting the model parameters. I discussed with you in details about regression, linear regression. In linear regression you have 2 model parameters, y is equal to w x plus b, w and b are the model parameters. We simply adjust these 2 model parameters so that we can reduce the difference between the predicted value and the actual value. So, virtually speaking, if your predicted value is p and actual value is this is the error, right, and we always talk about mean square error, that is nothing but 1 by n summation I j to 1 to n, okay, y p j y I j, right, that is what it is, square. So, we always try to minimize this mean square error. In order to do that, we use this technique called a gradient descent problem, right. So, we have discussed about that. So, now you can have this kind of problem where you have seen that this is what is, this is the minimum cost point. Slope is nothing but derivative or the first derivative rather. So, you can always go along the direction which is basically negative slope or positive slope or along these directions. You can always move along this direction also, right, you can clearly see, right. So, that is your negative slope, this is your positive slope, right. So, therefore, you can move both the direction and that is this is your incremental step, what is not a learning rate. So, finally, your goal is to reach this minimum cost point, and cost function is nothing but error function, right, we always discuss, please remember this, cost function is nothing but the error functions, and error is very important. You calculate the error, I will tell you in some of the lectures what are the difference of calculating errors. If you are not still finding out, please go back to my lectures on the machine learning course where we have discussed in details about many of these error functions. So, this is what it is, and the most important error is the mean square error. It is commonly used in regression problems. It basically takes the square of the difference between predicted and actual value and then average these by the number of times you are calculating, right. You otherwise you can use cross entropy or hinge losses, correct. The 2 important factors which decides or influence the gradient descent efficiency. First, the differentiability. Remember, when you have a function may be continuous, may not be differentiable at a particular point or a range of points, right. So, that is why gradient descent algorithm requires the cost function to be differentiable, and differentiable function always allows the computation of the gradient, and which is the required thing for finding the direction of the steepest ascent. You also need to know convexity. Okay, so remember, we are trying to find the minimum position or minimum value of the error, right, and as per calculus the minimum value can be determined by using both the first and the second derivative, right. First derivative tells you what? Tells you that what is the slope. Second derivative tells you the convexity, right. The cost function should ideally be convex to ensure the gradient descent can reliably be applied to find the global minimum, and convex function must have a second derivative that is non-negative. Remember this, non-negative or not 0. The second function must not be, so it must be greater than 0. This is what the condition, that is the condition of minimum, right. So, this is what your first derivative, this is what the second derivative. These two factors basically decide the efficiency of the gradient descent problem. Well, so that is about the initial part of the whatever we learned. I did a lot of mathematical part later on, please go through it. If you have any questions, you can always ask me or the TS also. So, material informatics action, next thing we are going to discuss is, we have started discussing about the ensemble learning. So, it is a basically composite model we discussed about, right. What did I say in the last lecture? Well, ensemble modeling is a committee based learning. What is the meaning of committee based learning? In this learning, a committee member, each community member is an individual learner with the best learning capability. Okay. That means, you have a community or you have a committee has many members, each member is basically considered as individual learner, also called a best learner, right, also called a best learner, remember this. And therefore, each one will learn from a best learning algorithm. So, what do you do? The predictions are basically, how it is done? Predictions are basically done by voting the weighted voting, given a voting or weighted voting of the learners. Remember that this is not average. When the learners are learning, you may say predictions will be average of all the learners, whatever they are providing, right. No, it is done by voting or average voting. That is what we will discuss today, how it is done both mathematically as well as physically. Remember these aspects. Now, if all the learners are using the same algorithm, let us say all the learners are using regression analysis, then it is called a homogeneous ensemble learning. If there are different learners are learning different kind of algorithms, then it is called heterogeneous learner. Someone is learning regression, someone is a Bayesian algorithm, someone is learning SVM, and you have to take the final outcome as a voting or average weighted voting of the each of this, then it is called a heterogeneous learning. Remember this. So, homogeneous learning means when all the learners are using same learning, the same algorithm, right. That is what is the very simplest way. If the learners are using different kinds of algorithm, then we call it heterogeneous learning. So, in case of homogeneous learning, you simply take average, right, very easy, but in case of heterogeneous learning, you have to use weighted average. That is why this weight factor comes into picture. So, you are putting some more importance on some model than some other model. That is why the weight factors comes into picture. So, it basically is a composite model which combines a series of low performing models or classifiers. Classifiers we already discussed, right, with the aim of creating an improved model or classifier, right. That is what it is, the main job. So, it is a composite model, it is basically committee based model. It combines a series of low performing classifiers or models. The individual classifier vote, individual classifier will vote, remember this, and final prediction return the model which performs, which gets the majority voting. Okay? That is what it is. So, this is distinctly different, remember this. So, individual classifier will vote, right, and the final prediction will provide that one that perform majority voting, correct. You understand that? That is a very important aspect. So, ensemble offer more accuracy, that is why than an individual or basic based learners, always it will provide you more accuracy. Ensemble methods can be parallelized also by simply allocating each base learner to different machines. We will talk about it. They can be parallelized, they can be series, both are possible. Ensemble learning methods are called meta algorithms. Why? Because they combine several machine learning methods into a single predictive model. And why do you do that? Idea is to increase the performance. That is what the idea is, to increase the efficiency of predictions. That is why I use ensemble learning, correct. I know this is something new to it, you may not have learned, but idea is very simple, right. We can always use one learning like regression or Bayesian or something else, or we can use many learning machines and then put them in a series or a parallel combinations, and finally, the outcome is based on the majority voting concepts. So, ensemble methods can decrease the variance. You may not have heard about variance now, variance by Bagging approach, bias using a boosting approach, or improve prediction using a stacking approach. So, you could understand there are three basic approaches, what is known as a Bagging approach, boosting approach, or stacking approach. You will soon learn how I am talking about these things very soon. Okay. So, I hope this is the very beginning of the ensemble learning. They are committee based learning, and which can put either series of low performing class models or put the low performing models into parallel combinations, okay, and into a single predictive model. So, that we can increase the performance, remember this, and final prediction is based on the majority voting. So, we can have three types of models basically, one is called boosting, other one is called bagging, and third one is called stacking. So, it is an art of combining diverse set of learners. This is also important. You need not combine only same set of learners, you always combine a diverse set of learners together to improve the stability and the prediction power of the model. Very interesting, is it not? So, you know that in real life also, suppose you are in a classroom, you can have different set of students learning topics in different way. So, like somebody may learn quickly, somebody may learn slowly, somebody may learn more, somebody may learn less. But when you combine them together and try to develop a combined model, that will be always more efficient, more predictive power than the individual ones. This is the idea, very simple idea, but very elegant idea. The simple power, we combine all the predictions collectively, that is why it is called ensemble learning, when you put things together. Okay. In thermodynamics, there is something called ensemble also, you can read it in statistical thermodynamics. So, ensemble based models can be incorporated in both in two scenarios, when data is large volume and when data is too little, both. That is also another advantage. Remember this is very important. So, ensemble models can be used in both situations, where you have more data or you have less data. So, therefore, you can solve any problems. We have a scarcity of data, that is what most of the material science problems are, or when you have huge amount of data, like in big data problems, both the cases you can use ensemble learning. That is the major advantage. Okay. This is one such thing. So, you can see there are various learners 1, 2, 3, 4, 5, 6, 7, 8, okay, and they are individually providing predictions, and then final prediction is decided by the voting. This is what the ensemble learning looks like. So, if I have to go to the board and discuss about that, so let me just go there and tell you that. Consider an ensemble learner, let us say ensemble learner G M X. This is an ensemble learner. That means, it includes M learners, right. G M X means it is good M learners, correct, and so each of these M learner is a base learner, and we can write down small g J X, right, where J can go 1 to M. We can easily write down like this is your ensemble learner. It consisting of M base learners, correct, and each base learner can be written as G J I G G G J X. Okay. So, you can always use equal weight. If you have equal weight learners, means what? Homogeneous learners. All of them are learning for the same kind of models. That is why I call equitable learners. Then G J G M X is nothing but sum it over J going to 1 to M G J X, right. That is what it is, because here every learner has equal weightage. Hence, every learner is equally important. So, when every learner is equally important, you simply sum it over across all the learners. Okay, if this base learners are same. So, basically let us say you are talking about all the base learners as regression learners, correct, a linear regression learner. Let us talk about simplicity, and each of them basically learning and predicting. So, what will happen? Your final prediction will be simply sum it over of all the learners. Now, if you have weighted learners, weighted based learners, then what will happen? If you use weighted based learners, then this GMX will change. This will become what? This will become sum it over J 1 to M alpha J GJ X, correct. For alpha J, obviously J varies, here also J varies 1 to M, here also J varies 1 to M, right. Can you see that very clearly? So, here alpha J is what? It's the weight of the jth base learner, weight of jth base learner. Am I clear? And this alpha may be different for each of the base learners. So, let us say for the first learner, for j equal to 1, this has a value of 1, let us say. For the second learner, it may have value of 3, correct. That is why this weighted factor comes into picture, remember this. So, this is your ensemble learner, okay. That is what it is. So, total learning capability is increasing extensively, remember these aspects, okay. So, there are basically, this is what I show you here in this slide also, you can clearly see that. So, P is the predictions and you have different X learners, correct. You can see X learners, no, X there is a P1, P2, P3, P4, P1, P2, P1 to P1 superscript 1, P1 superscript 2, P2 superscript 3, P2 superscript 1, and then it is a X1 and X, right, and then you have X1, X2, X3, X1, X2, and this is X3, right. I hope you can see it clearly. So, this together they are giving these functions and they are then combined by the weighted factors, and then that is why we find GM. So, let us just to give an idea, this is taken from the literature, taken from the book of T. Zhang, okay. T. Zhang's book, that is Introduction to Material Informatics, right. So, therefore, here you see you have a data and you have 4 different learners, Lazo already have learned, KNN, k nearest neighbor, SBR, support vector regression, random forest, correct. And when you combine them together, you get a meta learner and that provides the predictions. The ensemble learning is putting things together, right, hope you understand very clearly. So, that is the main idea, when you put things together, how these different learning, different what do I say, models they learn and then they put together things, but prediction is basically based on the voting, majority voting, okay. So, out of these 4 learners who have, let us say 3 are voting for something and 1 is voting for something else, you are going to consider the majority voting things, you are not going to consider the one which is voting, right. That is what is the predictions are decided. So, I hope I am clear what I am talking about it. What I am trying mean to say is that when you have a large data or small data, both the cases you can use different kinds of base learners, you can see these are the base learners and they learn from the data and then predict, and prediction is decided by majority voting idea, okay. So, this is the main concept by which ensemble learners lie, and as I said there are basically 3 types of ensemble learner we discuss, bagging, boosting and what, something else I told, bagging, boosting and stacking. Okay. 3 learners are there, but we are going to mostly focus on bagging and boosting. And these 2 major types of learning is called boosting and bagging. Boosting methods of ensemble learning behaves like many base learners in a series, okay. But the bagging one, the base learners are in a parallel conditions. You know this in electrical engineering, there is some series resistance and parallel resistance. So, bagging ones are basically like series resistance, and boosting ones are like a series resistance. Let me write down, boosting ones are like a series resistance. Oops, bagging ones, boosting ones, they actually are series, and bagging ones are parallel. That is how it is basically done. Okay, so that is the introduction of the ensemble learning. We stop here for the first part of the lecture. We will come back and discuss about more details about these boosting and bagging, and we will talk about ADA boosting at the end of the lecture.